Today I want to outline a really interesting application and use case with STK being used to model long-range communications, in particular an often overlooked or minimized area of shortwave radio. As you may know, shortwave radio has been around for a long time. In fact, it was heavily relied upon during World War II to provide necessary long-range communications and information relay. Today, shortwave radio is typically associated with hobbyist users, or maybe leveraged by countries to spread news and information to areas that might otherwise have limited or no internet access. The uniqueness lies in the frequency of the radio waves to essentially bounce off of our upper atmosphere like a reflection, and then arrive many thousands of miles away. Predicting this is a challenge as well, but there are models that take some of these conditions into account and provide a well-trusted predictive approach to radio signal propagation through atmospheric reflection. The most common is called VOACAP, which stands for Voice of America Coverage Analysis Program. In fact, STK incorporates this model when users need to explore signal propagation for over-the-horizon communications as well as over-the-horizon radar detections. Which are very cool applications, but difficult problems to model without trusted tools. In this quick demonstration, I'm going to model a real-world application with shortwave radio. In fact, the exact situation I'm going to model is a result of something I picked up on my own shortwave radio receiver. I was tuning through the dial and I picked up a broadcast which sounded peculiar to me since it was in two different languages, which sounded like Italian with Spanish translation over the top. Here's the actual recording of the reception on my own radio. I was curious, so I did some Googling to see what could have been based on the time and frequency. I learned it was likely the Vatican radio broadcast. This meant that I was picking up a signal coming from Italy all the way here in East Tennessee in the United States, which is pretty impressive. But I wanted to really understand how I was able to pick up that particular broadcast, so I turned to STK. Let me do a quick overview of my STK setup, and then we can look at some of the results and how some of the parameters were matched to those I found while researching the specifics of the Vatican radio broadcast station equipment, the antennas and their schedules. First, let's look at my own receiver. To make it simple and not show my own home to the entire world, I chose to place my modeled receiver on a nearby church, unironically a Catholic church, whose attendees may also be interested in the Vatican radio broadcast perhaps. But I placed my modeled radio at the top of the structure to emulate my own altitude where I picked up the actual signal in the recording we saw. I used the same frequency and modeled a simple dipole antenna, since my own radio uses a dipole antenna. I did minimize the efficiency a bit to try and account for the fact that my simple radio's antenna isn't perfectly tuned to that particular frequency, but instead is meant to be reasonably efficient across a broad range of frequencies. This seemed to be close enough. I then modeled the broadcast station in Italy where the Vatican radio is located. This is a large antenna array, many of which can be tuned and pointed and are used with the intent to maximize broadcasts in many different directions at different times based on their broadcast schedule. I did confirm that the same time day of my own reception aligned with their broadcast schedule and determined which antenna type and direction was responsible. You can see it here in STK modeled appropriately and pointed in a direction that should coincide with the Vatican's published information. It lines up quite well. I then turned to setting up the power, frequency, and other parameters that were easy to find online. I was then ready to look at the specific point-to-point communications analysis, but I had to ensure that I was using STK's VOACAP RF model and also that I was instructing that model to reference the appropriate sunspot number for that day and time. Point-to-point results in this report show the various link budget parameters and properties that were calculated through this analysis. And I could, of course, dig in further and look at which layers of the atmosphere were responsible for the reflected signals, how many bounces, and things like that. All that information is available to me if I want to explore it further. But I was quite satisfied with just looking at the signal quality predictions and validating that I was also able to receive that general quality of signal in the real world. I then used STK's coverage tool to explore what quality signal my modeled radio might receive across a much larger gridded area. You can see the colors of the coverage result indicated on the map and colored based on what I would expect my signal's audio quality to be. Just because I can receive it doesn't mean it will be crystal clear in quality, so I wanted to understand what something like that might look like. So I enjoyed using some of STK's RF modeling features to explore this particular simulation and do a bit of, reverse engineering using a digital modeling and simulation approach. I hope you found it interesting, and thanks for watching.